Imagine your car not just, avoiding obstacles, but actually understanding the intent of every pedestrian, every cyclist, every other vehicle in a really busy city intersection.
Oh,
Picture your smartphone, right? Recognizing a landmark instantly and giving you not just information, but real insights pulled from millions of images.
yeah, it's already happening.
Exactly. This isn't some far off sci-fi dream. It's the quiet, often invisible revolution of AI computer vision happening all around us. And it's fundamentally changing how machines perceive and interact with our world.
It really is. It's weaving itself into the fabric of how things work.
So let's unpack this. Today, we're doing a deep dive into the fascinating and, frankly, sometimes kind of mind-bending world of AI computer vision.
It definitely can be.
This tech is rapidly changing how machines, and by extension, how we interact with the physical world. Our mission here is to give you a strategic analysis, its present capabilities, its exciting future, and, maybe most importantly, its profound societal implications.
Right, because the implications are profound.
You'll come away from this not just, well-informed, but I promise you, with a completely new lens on the visual world around you. You'll start seeing it everywhere.
And to guide us, we've distilled the key insights from this exhaustive report, AI Computer Vision, Now and Beyond. It really meticulously deconstructs the whole field.
Okay. Yeah.
Everything from the foundational tech to its surprising cross-industry uses, its current limits, the big ethical challenges it throws up, and its really exciting future paths. We're going to pull out the critical nuggets for you.
Excellent. Let's kick things off with what we're calling the algorithmic eye. We need to really define what computer vision actually is and trace its pretty remarkable journey from abstract ideas to the real world powerhouse it is today.
Right. So at its core, computer vision is a field within AI
Yeah.
that lets computers derive meaningful information from visual inputs.
Okay, so images, videos, that kind of thing.
Exactly. Anything from static digital photos to live video streams. And the ultimate goal, which is what's really fascinating here, is to replicate and automate human visual perception, our ability to understand what we see.
So it's about teaching machines not just to see the pixels, but to observe and ultimately interpret what's going on.
Precisely, to make sense of it.
So it's way more than just capturing a picture then. It's taking that stream of visual data, understanding it, figuring out objects, analyzing scenes, and then critically pulling out actionable insights.
That's it, exactly. And getting here, well, it's been quite a journey, a real paradigm shift. If you go back to the 60s and 70s, the early days,
Yeah.
It was all about what we call classical rule-based approaches.
Rule-based, meaning humans had to tell the computer exactly what to look for.
Pretty much. Pioneers like the neuroscientist David Moore were key. They set up foundational ideas about how vision works hierarchically. But yeah, in practice, human experts had to manually design specific feature extractors.
So I'm picturing someone literally programming, okay, computer, this sequence of dark pixels next to light pixels is an edge, find edges. Handcrafting algorithms for basic stuff like lines, corners.
You've got it. It was painstaking. They developed things like sift features or Sobel operators for edge detection. And while these methods were crucial groundwork, they were also, well, brittle.
Brittle how? Easily broken.
Yeah. They really struggle with the complexity and, the sheer variability of the real world. A slight change in lighting, a different angle, maybe something partially blocking the view, it could completely throw off the system. They didn't generalize well.
Okay, so that was the old way. What changed? What really kicked off this modern era of computer vision we see now?
The big transformation was really lit by three things converging, mostly from the 1990s onwards. First, just the sheer explosion of visual data available on the internet, digital cameras everywhere. Suddenly, images and videos were abundant.
Right, data field.
Exactly. Second, computing power became much more accessible and powerful, especially specialized hardware like GPUs, graphics processing units.
Which turned out to be great for this kind of math.
Perfect for it. And third, the development of much more advanced machine learning algorithms.
Ah, okay. So this is where that pivotal shift happens. From explicit programming, telling it to the rules, to learning from data, the computer teaching itself.
That's the fundamental change. Instead of being programmed with fixed rules, systems could now learn to recognize patterns directly from vast amounts of example data. Labeled data, usually.
So you show it thousands of pictures of cats, labeled cat, and it figures out what catness looks like on its own.
Essentially, yes. This move from handcrafted features to features automatically learned from data was incredibly effective. I mean, to put it in perspective, accuracy rates for common tasks like object identification they shot up from maybe 50%.
50? That's barely better than guessing for some tasks.
Right, to over 99% accuracy in less than a decade for some benchmark challenges. We now have systems that, in specific narrow situations, actually outperform humans at visual recognition.
Over 99%. That's staggering. An incredible leap. So how does this modern AI-driven computer vision actually work day to day? Can we break down the main stages?
Sure. It generally boils down to three main stages. First is image acquisition, simple enough, just capturing the raw visual data.
Cameras, drones, medical scanners like MRI, CT.
Exactly. That's the input, just getting the picture or the video feed.
Got it. So you've got the raw visual info. Then what?
Stage two is the real core, image processing and analysis. This is where the AI models, mostly deep learning models these days, get to work. They meticulously analyze the pixels. They identify important features, recognize complex patterns, basically by comparing what they're seeing now to the vast knowledge they gain from being trained on millions, sometimes billions, of labeled examples.
So they're pattern matching on a massive scale based on prior learning.
In a sophisticated way, yes. And finally, stage three, image understanding and action. This is where it gets really interesting, moving beyond just seeing to interpreting and deciding.
Okay, so making sense of it all.
Exactly. The system interprets the processed information to derive meaning. It makes a classification or a decision, like identifying that specific person in a security feed, detecting that defect on a product line, classifying that tissue sample as cancerous.
And that understanding leads to what? An alert, an action.
It could be a recommendation for a human. Hey, look at this scan. Or it could trigger a fully automated action like stopping a conveyor belt or guiding a robot arm.
That makes perfect sense. Input, process, understand, act. So that's the high-level flow. But the real magic, the power, is how these systems learn to see and adapt. Let's pull back the curtain on the tech driving this. The relationship between AI, machine learning, deep learning. Can you clarify that hierarchy?
Yeah, it's helpful to see it as nested concepts. Artificial intelligence, AI, is the broadest field. It's really any technique enabling computers to mimic human intelligence in some way.
Okay, the big umbrella.
Right. Then machine learning, ML, is a subset of AI. ML focuses specifically on algorithms that let systems learn from data to make predictions or decisions without being explicitly programmed for every single scenario.
Learning from experience, essentially.
You got it. And deep learning. That's an even more specialized subset of ML. It's characterized by using artificial neural networks with many layers, hence deep. Computer vision, as an application of AI, relies very, very heavily on these deep learning algorithms today.
So deep learning is the engine for modern computer vision. What's so special about it for seeing? You mentioned end-to-end learning. What does that actually mean for someone building these systems?
End-to-end learning is a huge deal.
Yeah.
Remember how we said humans used to have to manually design feature extractors?
Right, telling the computer, look for edges, look for corners.
With deep learning, particularly with architectures like CNNs we'll discuss, you feed the system the raw data, literally the pixel values of an image, and you provide the desired output, like the label cat. The network then automatically discovers the most useful features needed to make that prediction correctly. It learns the hierarchy of features itself, from simple lines to complex shapes to whole objects.
So it figures out what visual patterns matter most for telling a cat from a dog without a human explicitly coding those patterns.
Exactly. It learns the features and the classification logic all in one go, end to end.
So what does this mean for the people involved? The expertise required must have shifted dramatically.
It really has. The focus moved away from needing deep, domain-specific signal processing knowledge to handcraft features. Now it's much more about data science skills.
Like what?
Collecting and cleaning massive data sets, ensuring they're well-labeled and representative. Designing effective neural network architectures, deciding how many layers, what types of layers, and carefully tuning the whole training process, which is almost an art form in itself.
So it's more about managing the learning process and the data rather than defining the visual rules up front.
Precisely. And this abstraction, this removal of the need for handcrafted feature engineering, has, in a way, democratized the development of really powerful vision models. More people could build them.
That sounds incredibly powerful. But you mentioned a black box problem earlier. Does this end-to-end learning contribute to that? Is that the downside?
It absolutely contributes. It's a major downside. While these deep models are incredibly powerful, their internal decision-making process can become extremely opaque. It's hard, sometimes impossible, to know exactly why the model made a particular prediction.
Even for the engineers who built it.
Even for them. This lack of interpretability creates huge problems for trust, for accountability, especially in high-stakes areas like self-driving cars or medical diagnosis. If something goes wrong, how do you debug it? Who's responsible? It's a critical limitation we definitely need to circle back to.
Okay, duly noted. Now, let's talk about the architecture that's been the real workhorse for so long. Convolutional neural networks, CNNs. How do they work? Why are they so good at processing images?
CNNs really dominated computer vision for, well, the better part of a decade, starting around 2012. And they're so effective because their architecture is specifically designed for grid-like data, like pixels in an image. What's really cool is that their design is biologically inspired.
Inspired by how our own brains see.
Yeah, by the animal visual cortex.
Hmm.
In our brains, individual neurons only respond to stimuli in a small, restricted region of our visual field. It's called a receptive field. CNNs mimic this idea of local connectivity.
So it's not looking at the entire image all at once. It focuses on small patches, like our eyes scanning.
Exactly. The core building block is the convolutional layer. Think of it as applying a set of learnable filters, or kernels, across the input image. Each filter is like a tiny pattern detector. Maybe one looks for horizontal edges, another for a specific texture, another for a green blob. These filters slide across the image, performing a mathematical operation called convolution at each position. This creates activation maps or feature maps that highlight where those specific features were detected in the image.
So you get maps showing edges here, textures there.
Pretty much. And a key concept here is shared weights. The same filter with the same learned weights is used across the entire image. This drastically reduces the number of parameters the network needs to learn, making it much more efficient and helping prevent overfitting. It assumes that if a feature is important in one part of the image, it might be important elsewhere too.
That makes sense. Fewer things to learn. What comes after the filters?
After the convolution, you usually apply an activation function, most commonly ReLU, rectified linear unit. This introduces nonlinearity into the model. Images and the real world are inherently nonlinear, so this step is crucial for the network to learn complex patterns beyond simple linear combinations.
Right. The world isn't just straight lines.
Exactly. Then, often you have pooling layers, especially max pooling.
Pooling. What's that for?
Pooling layers progressively reduce the spatial dimensions, the height and width of the feature maps. Max pooling, for instance, takes a small window of the feature map and just keeps the maximum value, discarding the rest.
Why do that? Doesn't that throw away information?
It does lose some information, but it serves several important purposes. It makes the representation more compact, reducing computation and the number of parameters further down the network, again helping control overfitting. It also provides a degree of translation invariance.
Translation invariance. You mentioned that. What does that mean again? It doesn't matter exactly where the feature is in that small window.
Right. It makes the network more robust if the feature shifts slightly. Whether the edge is in the top left or bottom right of that small pooling window, max pooling will likely still pick it up.
Okay, so you stack these layers. Convolution, activation, pooling, and that lets the network learn more complex things. That's the hierarchical feature learning.
Precisely. That's the real beauty of CNNs. The first few layers might learn very simple features, edges, corners, colors. Layers deeper in the network combine these simple features to learn more complex patterns, maybe textures, simple shapes, parts of objects like an eye or a wheel.
And then eventually, whole objects.
Exactly. The deepest layers combine these mid-level features to recognize entire objects, like a face, a car, or a cat. Finally, you usually have fully connected layers at the end, which take these high-level features and perform the final classification, outputting the probability that the image contains a specific object.
It really is like building up understanding layer by layer. It's fascinating how it mirrors biological vision concepts, where there's specific CNN architectures that marked big milestones.
Oh, absolutely. The field leapfrogged through key innovations. AlexNet in 2012 was the big bang, really. It won the ImageNet competition by a huge margin and showed the world the power of deep CNNs trained on GPUs. That kicked off the deep learning revolution.
I remember hearing about that one.
Then came others like VGGNet, which showed that simply making networks deeper with very small, simple filters could be very effective. GoogleNet introduced inception modules, which were clever ways to be more computationally efficient while capturing features at multiple scales.
And ResNet, that one comes up a lot.
ResNet, or residual networks, was another massive breakthrough. It introduced residual connections, or skip connections, which allowed networks to be trained much, much deeper, hundreds, even over 1,000 layers deep, without succumbing to the vanishing gradient problem, where the learning signal gets lost in very deep networks. ResNet architectures are still widely used as backbones today.
It shows how much progress relies on clever architectural ideas, not just brute force computation.
Absolutely. Smart design is crucial.
But AI never stands still. CNNs were dominant, but is anything new challenging them now? Something maybe taking a different approach?
There is. While CNNs are still incredibly important and widely used, the transformer architecture has made huge waves. It completely took over natural language processing, and now it's been successfully adapted for vision tasks, too, in the form of the vision transformer, or ViT.
Transformers for images. How does that work? I thought they were for sequences, like words in a sentence.
That's the clever part. Instead of CNNs sliding local filters, a ViT takes a different route. It splits the input image into a grid of fixed-size patches, say 16 by 16 pixels each.
Okay, like tiling the image.
Exactly. Then it flattens each patch into a long vector, adds some positional information so the model knows where each patch came from, and treats this sequence of patch vectors just like a sequence of word embeddings in NLP. It feeds this sequence into a standard transformer encoder.
And the key transformer ingredient is that self-attention mechanism, right? How does that apply to image patches?
Yes, the core is the multi-head self-attention mechanism. What's fascinating here is that it allows the model, when processing one image patch, to look at all the other patches and weigh their importance or relevance.
So a patch of sky can pay attention to a patch of a bird flying in it, even if they're far apart in the image.
Precisely. This enables ViTs to learn long-range dependencies in global relationships between different parts of the image directly, which is something CNNs, with their inherently local receptive fields, have to build up layer by layer.
That sounds like a fundamentally different way of seeing.
It is. It's a significant paradigm shift.
Mhm.
It shows this amazing cross-pollination between AI domains, ideas from language processing transforming vision. And it strongly suggests the future might lie in hybrid models, maybe combining the local feature extraction strengths of CNNs with the global relationship modeling of transformers. Research is very active there.
Fascinating. Okay, so we have these powerful engines, CNNs, ViTs, maybe hybrids. Let's talk about what they actually do. You mentioned a sort of taxonomy of vision tasks, the building blocks for all the sophisticated applications. Can you walk us through those key capabilities?
Right, these core tasks are the foundation. First, maybe the simplest, is image classification.
Just assigning a single label to the whole image.
Exactly. Is this a picture of a cat or a dog? Or in medicine, is this X-ray showing pneumonia or not? Social media tagging is another big one. The system answers, what is this image?
Okay, simple label. What's next?
Object detection. This goes a step further. It doesn't just classify the image, it finds where specific objects are within the image and classifies each one.
Yeah, so drawing the bounding boxes.
Right. It outputs bounding box coordinates and a class label for each detected object. So not just there's a car in the image, but there's a car here, a pedestrian there, and a traffic light over there.
Crucial for autonomous vehicles, obviously. Or retail shelf monitoring, quality control.
Exactly. Then, if you need to follow those objects over time in a video, you have object tracking.
Keeping track of the same object from frame to frame.
Yes. It takes the detections from object detection and links them across frames, maintaining a consistent ID for each object as it moves or changes appearance. Think security surveillance following a person, or sports analytics tracking a player's movement on the field.
Got it. What about getting even more precise than a bounding box?
That's image segmentation. This provides a much more detailed understanding. Instead of just a box, it assigns a class label to every single pixel in the image.
Pixel level classification. Wow.
Yeah, so you get precise outlines of objects. There are different types like semantic segmentation, where all pixels belonging to the same class, for example, all cars, get the same label, or instance segmentation, which distinguishes between different instances of the same class, for example, car 1, car 2, car 3.
Where would you use that level of detail?
Medical imaging is a huge one, precisely outlining tumors for radiation planning or organs for surgical guidance. Autonomous driving uses it to delineate the exact drivable road surface, lane lines, sidewalks. Augmented reality uses it to separate people or objects from the background accurately.
Okay, very precise. What else is in the toolbox?
Optical character recognition, or OCR. This is specifically about extracting text from images.
Like reading a license plate or digitizing scanned documents.
Exactly. Converting pixels that form characters into actual machine-readable text data. Very important for automation in many industries.
And then there's the one everyone talks about, facial recognition.
Right. It's really a specialized form of object detection and recognition focused solely on identifying or verifying individuals based on their facial features.
Phone unlocking, security access, border control. Lots of applications and lots of controversy we'll get into.
Indeed. Moving beyond individual objects, we have scene understanding. This is about interpreting the broader context of an entire image or video scene.
So not just there's a person in a car, but a person is getting into a car on a city street at night, understanding relationships and activities.
Precisely. It involves reasoning about the interactions between objects, the overall environment type, the actions taking place. Think smart cities analyzing traffic patterns and pedestrian flows, or content moderation systems identifying complex events in videos.
And finally, something a bit different. Image generation and enhancement. This isn't just analyzing, it's creating or improving images.
Yes. This includes generating entirely new synthetic images, often used for data augmentation, creating more training examples. Or enhancing existing images, things like super resolution to make blurry images sharp, denoising to remove graininess, or even image colorization.
So the creative side of computer vision. Generating realistic faces, upscaling old photos, creating art.
All of that falls under this umbrella. These core tasks are the building blocks that get combined in sophisticated ways to create all the applications we see.
Right, which is a perfect segue. Now that we have the tech foundation, let's explore where computer vision is actually making an impact today. You said it's touching nearly every major industry.
It really is pervasive. Automating visual tasks, boosting safety, unlocking efficiencies. Let's start with healthcare and life sciences. This is a huge area.
Augmenting human diagnosis, you mentioned?
Yes, that's the key phrase. It's about assisting medical professionals, not replacing them. Revolutionizing diagnostics, treatment planning. It excels at analyzing medical imagery, X-rays, CT scans, MRIs, pathology slides to spot anomalies with incredible speed and consistency.
Sometimes even better than humans in specific tasks.
In certain narrow, well-defined tasks, yes, AI doesn't get tired or distracted. It can help clinicians manage overwhelming workloads, potentially reduce diagnostic errors, and enable earlier detection, which is often critical.
That's a crucial point, earlier detection. Let's focus on a specific case. Advanced cancer detection. What's the core problem CV is tackling there?
The challenge is immense. Manually reviewing medical images looking for subtle signs of cancer is incredibly demanding. It takes years of training, it's time-consuming, and even for experts, there's inherent variability. Fatigue plays a role, and tiny, early-stage indicators can be missed.
And the consequences of missing something are obviously huge. So how do deep learning models help?
Deep learning models, especially CNNs, are trained on enormous data sets, millions of images showing both healthy and cancerous tissues. They learn the incredibly complex visual patterns associated with different cancer types, often patterns too subtle for the human eye to consistently catch.
And they use multiple CV tasks to do this.
Yes, they'll use image classification as this scan overall benign or malignant. Object detection, where the potential tumor is located, drawing bounding boxes, and crucially, image segmentation, mapping the exact boundary of the tumor pixel by pixel.
That segmentation must be vital for planning treatments like radiation, right? Targeting the cancer while sparing healthy tissue.
Absolutely essential. And the results have been pretty remarkable. For lung cancer detection from CT scans, models have shown accuracy rates up around 95%.
Wow. And I remember the Google Health study on breast cancer.
Yes, that was a landmark paper. Their AI system was compared against human radiologists interpreting mammograms. The AI showed a significant reduction in both false positives flagging cancer when it's not there by 5.7% and false negatives missing cancer when it is there by 9.4%.
Reducing both types of errors is huge. Fewer unnecessary biopsies and catching cancers earlier.
Exactly. It directly impacts patient outcomes and reduces anxiety.
Are there other cutting-edge examples beyond just detection? You mentioned one, the Chief model.
Right. There are mobile apps like Skin Vision using AI for skin cancer detection from photos, claiming high accuracy. But what's really interesting are models like Chief. It was trained on a massive data set, 15 million unlabeled images, plus 60,000 labeled pathology slides. It achieved 94% accuracy across 11 cancer types.
Okay, impressive accuracy. But you said it does more.
Yes, this is where it gets really fascinating. Chief can go beyond just saying cancer or no cancer. It can actually predict things like the tumor's molecular profile, which can guide targeted therapies. It can even forecast patient survival rates and how likely they are to respond to certain treatments, all just from analyzing the image of the tumor cells.
That's incredible, extracting that much information from pixels. So strategically, what's the impact in healthcare? How is it changing practice?
It's streamlining workflows. AI can act as a tireless second reader or a triage tool, flagging suspicious scans for human experts to prioritize. This speeds things up like a 30% faster turnaround for chest x-rays in one study. It lets specialists focus their valuable time on the most complex cases, leading to faster diagnoses overall and better patient outcomes.
Okay, from the human body, let's shift gears dramatically to the automotive industry. Computer vision is obviously fundamental for autonomous mobility.
It's the primary sensory system for self-driving cars and advanced driver assistance systems, EAS. It's what allows the vehicle to see and interpret its incredibly complex and dynamic environment in real time.
And the obvious case study here is Tesla and their vision-first approach. What's the main challenge for autonomous vehicles that CV solves?
The core challenge is achieving a comprehensive, real-time 3D understanding of everything happening around the vehicle. It needs to reliably detect and classify everything: other cars, trucks, pedestrians, cyclists, lane lines, traffic signals, road signs, construction zones, debris, you name it, and predict what they might do next, all for safe navigation.
Now, Tesla's approach is controversial because they're vision only, right? They ditched radar and never really used LiDAR like many competitors do.
That's their big bet. They argue that humans drive primarily with vision, two eyes, so a sufficiently advanced AI vision system, powered by cameras and massive neural networks, should be able to do the same, or even better. They see LiDAR and radar as costly crutches that add complexity and might offer a false sense of security.
So their system relies purely on cameras. How many and how is it processed?
Their autopilot and full self-driving FSD systems use a suite of 8 cameras around the car, providing a 360-degree view. These video streams are the only sensory input for the perception system. This data gets fed into a powerful, custom-designed onboard computer, the FSD chip, which handles the immense processing load.
And they have this HydroNet architecture. It sounds complex.
It is. It's a single, large, unified deep neural network. It has a shared backbone, kind of like ResNet, that extracts features from all 8 camera feeds simultaneously.
Okay, processing everything together.
Right. These features are then fused into a unified bird's-eye view representation of the world around the car, often using transformer-like mechanisms to understand spatial relationships. This unified view then feeds into numerous specialized heads, smaller networks, each focused on a specific task.
Like one head for detecting cars, one for lane lines, one for traffic lights.
Exactly. Detecting vehicles, pedestrians, lanes, traffic signals, road edges, drivable space, dozens of tasks, all running in parallel off that shared backbone. It's a very efficient multitask learning setup.
What's the most critical piece of their strategy, though? Is it just the vision-only tech or something else?
I think the real competitive moat for Tesla is their data engine. Every single Tesla customer driving with autopilot or FSD enabled acts as a data collection sensor.
Ah, the fleet learning.
Yes, they constantly encounter rare, unusual, challenging edge cases on the road, weird lighting, complex intersections, unexpected obstacles. This data gets uploaded, automatically flagged if the system struggled, and used to create new training examples to improve the neural networks.
Creating a continuous improvement loop.
A massive one. Fleet collects data, data improves AI models, improved software gets pushed back to the fleet via over-the-air updates. The smarter fleet collects even better, more targeted data. This fleet leverage is incredibly difficult and expensive for competitors, especially startups, to replicate at scale.
That makes sense. It's a powerful flywheel. But it also puts enormous pressure on the vision system, right? If the cameras fail or get confused, there's no backup from LiDAR or radar.
Absolutely. It's a high-stakes strategy that demands extremely high robustness and reliability from their computer vision algorithms. There's less redundancy.
Okay, from driving to shopping. Retail and commerce. Another area seeing huge change from CV.
Definitely. It's driving digital transformation across the board, streamlining operations in warehouses and stores, reducing theft and losses, and creating much smoother customer experiences, everything from inventory management to analyzing shopper behavior.
And the prime example everyone points to is Amazon Go's just walkout stores. What was the problem they were trying to fix there?
The core problem was checkout friction. Waiting in line is consistently one of the biggest pain points in retail. It leads to frustration, abandoned purchases, and requires significant labor costs for cashiers. Amazon wanted to eliminate that friction entirely.
And their solution involves a sophisticated mix of computer vision and other sensors. You called it sensor fusion.
Exactly. Amazon Go is a brilliant example of sensor fusion. Combining data from multiple sensor types, primarily cameras and weight sensors, to get a much more accurate and robust understanding than any single sensor could provide alone.
So walk me through it. I enter an Amazon Go store. What happens?
You identify yourself at the entry gate. usually by scanning a QR code in the Amazon app, tapping a credit card, or even scanning your palm with Amazon One. The system assigns you a temporary, anonymous digital ID for that shopping trip linked to your account.
Okay, I'm in the system. Then what? The ceiling cameras take over?
Pretty much.
Right.
There's a dense array of cameras mounted on the ceiling, continuously tracking everyone in the store. They're performing several complex CV tasks in real time. Person detection and tracking figures out who is who and where they are, even when people walk close together or temporarily block each other from view handling occlusions and tangled states. Pose estimation analyzes body posture, especially arms and hands, to figure out if you're reaching for an item, picking it up, or putting it back down. And object recognition using CNNs identifies the specific products being interacted with, even distinguishing between very similar-looking items.
But it's not just the cameras, right? You mentioned weight sensors. That's the fusion part.
Crucially, yes. The shelves themselves are equipped with weight sensors or load cells. So when you pick up, say, a can of soup, the cameras see you perform the action, and the shelf sensors detect the corresponding decrease in weight at that specific location.
Ah, so it cross-references the visual action with the physical weight change.
Exactly. This fusion provides vital redundancy. If the camera view is briefly blocked, the weight sensor still registers the change. If someone picks up an item and puts it back in the wrong place, the system knows which item was removed based on weight, even if the cameras didn't see it placed back correctly. It resolves ambiguities and ensures very high accuracy.
And all this feeds into my virtual cart automatically.
Precisely. As you take items, they're added to your virtual cart. If you put something back on the shelf, any shelf, it's removed from your cart.
What's really fascinating here is how they train these systems. I heard they rely heavily on synthetic data. Can you explain that?
Yes, that's a key enabler, especially for scaling up. Amazon uses generative AI techniques to create vast amounts of synthetic, photorealistic, but completely computer-generated training data.
So fake shoppers in fake stores picking up fake products?
Yep. Essentially, yes. But crucially, this synthetic data comes perfectly labeled automatically. The system knows exactly who picked up what, where every joint on their virtual body is, what every pixel corresponds to. Generating this avoids the incredibly expensive and time-consuming process of collecting and manually annotating real-world video footage.
So what does this mean for you if you're Amazon? Faster rollout.
Much faster rollout. It allows them to train models for new store layouts, new product types, and a huge variety of potential shopper behaviors and edge cases before a store even opens, without needing tons of real-world data from that specific store first. It dramatically accelerates development and improves robustness.
And then when I'm done shopping, I just leave.
You just walk out. As you exit through the gates, your session closes, your virtual cart is finalized, and your linked payment method is automatically charged a few minutes later. You get a digital receipt.
The strategic impact seems obvious for the customer pure convenience. What about for Amazon or other retailers adopting similar tech?
It's huge. Eliminating checkout boosts customer throughput. Staff can be redeployed from cashiering to more valuable tasks like stocking shelves or assisting customers. And importantly, it generates an incredibly rich stream of anonymized data about how shoppers interact with products, shelf layouts, and store flow, which can be used for optimizing everything from inventory management to store design.
Okay, next up, a sector where CV is both powerful and controversial: security and public safety. This is where it becomes that double-edged sword, especially with facial recognition.
Indeed. Facial recognition is probably one of the most widely known CV applications, and definitely the most debated. It's used for everything from unlocking your phone to large-scale government surveillance systems.
Let's use airport security as a case study. What's the problem these systems are trying to solve there?
The main challenge has always been the bottleneck created by manual identity verification checking passports and boarding passes. It's relatively slow, prone to human error, and potentially vulnerable to people using fraudulent documents.
So the CV solution is to automate that check using faces. How does it work practically, say, at border control or boarding?
Increasingly, agencies like the TSA in the US or border forces globally are deploying facial recognition. Typically, a camera captures a live image of your face as you approach a gate or counter. This live image is then compared against a trusted, pre-existing photo stored by the government, usually for your passport or visa application.
And the tech creates a unique face print.
Yes. The system analyzes your facial features, distances between eyes, shape of nose, jawline, etc., and converts these into a unique numerical code, a template, or face print. Powerful matching algorithms then compare the face print generated from the live image to the face print from the stored photo database.
And the accuracy's gotten really good.
Dramatically better. State-of-the-art algorithms now achieve very high accuracy, often exceeding human performance on standardized facial recognition tests. And they don't suffer from fatigue or the potential biases that can affect human inspectors.
So what are the claimed benefits? Speed, security.
The main benefits touted are efficiency and potentially enhanced security. Processing times can be significantly reduced, maybe from 16 seconds per passenger with manual checks down to 7, or even 3 seconds with automated gates. That means shorter queues, smoother passenger flow, and potentially lower staffing costs. Proponents also argue it makes it harder to travel using lost, stolen, or forged identity documents.
But this raises that important question, the double-edged sword. What are the big concerns here?
This application perfectly highlights the tension. The efficiency and security benefits are clear, but deploying facial recognition widely, especially in public or semi-public spaces like airports, raises profound questions about privacy, data security, and the potential for mass surveillance.
Concerns about where that biometric data goes, who accesses it, how long it's kept.
Exactly. How secure are these massive databases of face prints? Could they be hacked or misused?
Sure.
And fundamentally, does this technology represent an unacceptable step towards automated, pervasive government monitoring of citizens' movements and activities? It's a critical societal debate with no easy answers.
Absolutely. Okay, shifting away from consumer and public spaces, CV is also transforming more foundational industries like manufacturing and agriculture.
Yes, significantly. In manufacturing, computer vision is really the engine driving the smart factory concept.
How so? Quality control.
Automated quality control is a huge one. High-speed cameras paired with AI on assembly lines can inspect thousands of parts per minute, detecting tiny defects, scratches, misalignments, or cosmetic flaws with far greater speed and consistency than human inspectors.
Which leads to higher quality products, less waste.
Right, and faster production cycles. It's also used for predictive maintenance, visually monitoring machinery for subtle signs of wear or impending failure, allowing maintenance before a costly breakdown occurs. And it provides the eyes for robots.
Guiding robotic arms.
Exactly. Enabling robots to perform complex tasks like welding, painting, pick-and-place assembly, or bin picking with much greater precision and flexibility because they can see and adapt to variations in the parts or environment.
And in precision agriculture, how is CV changing farming?
It's enabling much more targeted, efficient, and sustainable farming practices. Drones or cameras mounted on tractors can survey vast fields.
What are they looking for?
Many things. Crop health monitoring by analyzing leaf color and texture for signs of disease, pests, or nutrient deficiencies. Yield prediction. But a really impactful one is weed detection.
Spotting weeds among the crops.
Yes. Deep learning models like YOLO or ResNet variants have achieved very high accuracy, up to 99% in some studies, at distinguishing weeds from crops. This allows smart sprayers to apply herbicide only to the weeds themselves, pixel by pixel, instead of blanket spraying the entire field.
That sounds like it could dramatically reduce chemical use.
Hugely. Reductions of 70–90% in herbicide use have been reported in some cases. That's a massive win for cost savings, environmental protection, and potentially consumer health. It also helps combat herbicide-resistant weeds. CV enables that level of precision.
Amazing. It's also used for automated harvesting, right? Like robotic fruit pickers.
Yes, there's another growing area, guiding robots to identify and gently pick ripe fruits or vegetables.
Okay, finally, let's touch on environmental stewardship. How is CV giving us a new perspective on the planet's health?
It's becoming a really powerful tool for monitoring environmental changes at scales that were previously impossible. It helps automate the analysis of the massive amounts of visual data we get from satellites, drones, and ground-based cameras.
What kinds of things can it monitor?
Tracking deforestation is a big one. AI analyzing satellite imagery can detect illegal logging or clear-cutting patterns much faster, sometimes in near real time, allowing for quicker responses. It can monitor water quality by analyzing color changes, indicating pollution or algal blooms. It can track air pollution plumes.
What about wildlife conservation? That seems like a natural fit.
Absolutely. Analyzing footage from camera traps spread across vast wilderness areas used to be incredibly tedious work for biologists. Now, AI can automatically classify the species caught on camera, count individuals, track population trends, monitor migration patterns, even detect poaching activity, all with much less human effort and disturbance to the animals.
Is there a specific example of using CV for monitoring climate change impacts?
Yeah, a really interesting one is the Berkeley RWWC project. They use a novel CV algorithm applied to microwave satellite data.
Microwave. Why microwave?
Because microwaves can see through clouds and dense forest canopies, which often block the view for regular optical satellites, especially in the tropics. This system can accurately map and monitor the seasonal flooding patterns of inland rivers and wetlands in these critical regions.
And why is that important?
This data is vital for improving flood prediction models in vulnerable tropical areas. And because wetlands are a major source of methane, a potent greenhouse gas, accurately mapping their extent and dynamics helps scientists better model and understand methane emissions as the climate warms. It's a unique insight enabled by combining CV with the right sensor data.
So looking across all these diverse applications, healthcare, automotive, retail, security, manufacturing, agriculture, environment, what's the big picture? What's the overall strategic impact of computer vision?
The common thread is the automation of tasks that traditionally relied on trained human visual inspection and judgment. Think about radiologists, factory inspectors, farmers scouting fields, security guards watching monitors. These jobs often involve repetitive visual search, require sustained attention, and are prone to fatigue and human error.
And CV offers superhuman capabilities?
Not necessarily superhuman intelligence across the board, but definitely superhuman endurance, consistency, and scale for specific visual tasks. And AI doesn't get bored or tired inspecting the millionth widget. It applies the same criteria every single time. This is fundamentally changing the nature of work in many fields.
How so? Is it just about replacing humans?
It's more of a shift. The role of the human expert often evolves from being the primary performer of the visual task to becoming the supervisor of the AI system. They train the AI, monitor its performance, handle the complex edge cases or ambiguous situations that the AI flags for review, and make the final critical judgments. But the routine visual work gets automated.
That has massive implications for workforce training, skill requirements, job design.
Absolutely. It requires retraining, upskilling, and rethinking workflows. It's a major transformation with broad economic and social consequences.
Okay, it's clear the promise is enormous. But we have to confront the other side of the coin, the perils. This tech presents a classic dual-use dilemma. Let's dive into that strategic reckoning, balancing the promise against the very real operational hurdles and the complex challenges.
You're right. For anyone leading a business or making policy, a clear-eyed view of both the upside and the downside is absolutely essential. Let's start by recapping the value proposition, the quantifiable benefits.
Right. What are the core strategic advantages driving adoption?
First and foremost, increased efficiency and automation. Automating those repetitive visual tasks we talked about, quality control, inventory checks, data entry from documents via OCR. This directly leads to labor cost savings and frees up human workers for higher value activities. Second, improved accuracy and precision. In many well-defined structured tasks, CV systems can simply be more accurate and consistent than humans. No fatigue, no distraction. This means higher product quality in manufacturing, potentially more reliable diagnoses in healthcare, more consistent monitoring and security. Third, enhanced safety and security. This is a massive driver in automotive, with ADS features preventing accidents. In factories or construction sites, CV can monitor for safety protocol violations or detect hazardous situations, preventing injuries.
And it's not just about optimizing existing things, but enabling totally new stuff too, right?
Exactly. Fourth is new revenue streams and enhanced customer experiences. Computer vision makes entirely new business models possible, like Amazon Go's checkout-free stores. Or think about virtual try-on for clothes or furniture online, which improves customer engagement and reduces returns. It's enabling innovation. And finally, data-driven decision-making. This is crucial. CV turns the visual world, which is mostly unstructured data, into structured, analyzable information. Retailers get data on shopper paths, cities get data on traffic flow, farmers get data on crop health. This leads to better insights and smarter strategic decisions.
Those benefits are definitely compelling. But what about the roadblocks, the real operational headwinds and technical limitations that companies hit when they try to implement this stuff? What are the big ones?
These are significant hurdles. Number one is data dependency and cost. Modern deep learning models are incredibly data hungry. They often need millions, sometimes billions, of accurately labeled examples to train effectively.
And getting that data is hard.
It's a massive bottleneck. Collecting the raw data can be difficult. Cleaning it is time-consuming. And annotating it, labeling every object or pixel, is extremely labor-intensive and expensive, especially if you need domain experts, like radiologists annotating medical images. This whole data dilemma can make building custom CV solutions prohibitively costly for many organizations.
So the garbage in, garbage out principle applies strongly. Even with great algorithms, bad or insufficient data is a killer. What about making them work reliably in the real world?
That's the second major challenge, robustness and generalization. A model might achieve 99% accuracy in the lab on a clean data set, but then its performance plummets when deployed in the wild.
Why? What kinds of things trip them up?
The real world is messy. Variations in lighting shadows, glare, fog, rain can drastically change how things look. Occlusion is huge objects being partially or fully hidden behind other things. That's critical for self-driving cars needing to see a pedestrian stepping out from behind the park fan. Viewpoint and scale variations, an object looks very different up close versus far away, or from different angles. Models often struggle to generalize well across all these variations if they weren't adequately represented in the training data.
And failures in generalization aren't just annoying, they can be dangerous.
Absolutely. In safety-critical applications like autonomous driving or medical diagnosis, a failure to generalize correctly can have catastrophic consequences. Ensuring robustness across diverse real-world conditions is a massive ongoing research and engineering challenge.
What about the sheer cost of running these things, computationally?
Yeah, computational and energy costs are a big factor. Training these huge deep learning models requires immense computational power, usually fleets of expensive GPUs, and consumes substantial amounts of electricity. That's costly and has environmental implications.
And running them, say, on a phone or in a car.
That's inference. Deploying complex models for real-time inference on resource-constrained edge devices like smartphones, drones, cars, smart cameras is really tough. You have to make difficult trade-offs between the model's accuracy, its speed, latency, its power consumption, and the hardware cost. Optimizing for the edge is a whole field in itself.
Then there's that issue we flagged earlier, interpretability, the black box problem. That seems like a fundamental trust issue.
It really is. Many of the most powerful deep learning models operate as black boxes. Because of their complexity, with millions or billions of parameters interacting in nonlinear ways, it's often impossible to fully understand why the model makes a specific decision or prediction.
So if a self-driving car causes an accident or an AI medical diagnosis is wrong, you can't easily trace the error.
It can be incredibly difficult. You can't easily pinpoint the faulty reasoning step. This creates a crisis for accountability: who is responsible. It hinders debugging and improvement. And fundamentally, it undermines user trust. If you can't understand how a system works, especially for critical decisions, it's hard to rely on it. What's fascinating here is how this technical limit directly fuels ethical concerns.
Definitely. And one more technical challenge, vulnerability to adversarial attacks. That sounds quite worrying.
It is a significant security risk that researchers have demonstrated. Adversarial attacks involve making tiny, often mathematically calculated changes to an input image changes that might be completely imperceptible to a human eye.
Like changing a few pixels.
Exactly. But these subtle changes are specifically designed to fool the AI model, causing it to make a confident but completely wrong classification. For example, researchers have shown you can put small stickers on a stop sign in a way that makes a self-driving car's vision system confidently classify it as a speed limit sign.
Wow. That's deeply concerning for safety and security systems.
It is. It highlights that these systems, despite their power, can be brittle in unexpected ways and potentially vulnerable to malicious manipulation if not properly defended.
So these technical limitations, data hunger, robustness issues, the bicortic adversarial vulnerability, they aren't just engineering problems. They feed directly into the ethical minefield, the broader societal risks and responsibilities.
They're absolutely intertwined. You can't separate the technical limitations from the ethical challenges. Deploying this powerful technology at scale forces us to confront really difficult questions about fairness, privacy, accountability, and potential misuse. And failing to address these proactively isn't just bad ethics, it's bad strategy. It risks public backlash, regulatory crackdowns, and ultimately could stifle beneficial innovation.
And you mentioned the pacing problem, technology advancing much faster than our ability to govern it.
That's a core issue here. AI capabilities are leaping forward exponentially, while our legal systems, regulations, and social norms struggle to keep pace. This creates a gap, a volatile environment where risks can emerge faster than we can manage them. It also leads to a fragmented patchwork of regulations across different regions, which is a nightmare for global companies trying to comply.
Okay, let's break down the key ethical risk categories. These seem critical for everyone to grasp. First, algorithmic bias and discrimination.
This is a huge one. AI systems learn from data. If the data they're trained on reflects existing societal biases, and real-world data almost always does, to some extent the AI model can learn, perpetuate, and often amplify those biases.
How does that manifest?
It can lead to systems that perform significantly less accurately for certain demographic groups compared to others based on race, gender, age, even things like skin tone or income level reflected in the data. This disparity in performance can lead to unfair or discriminatory outcomes when the system is deployed.
And we have concrete examples of this, especially with facial recognition.
Yeah. Yes, unfortunately. A major study by NIST, the U.S. National Institute of Standards and Technology, evaluated dozens of commercial facial recognition algorithms. They found many systems exhibited significant demographic differentials, with substantially higher false positive rates, incorrectly matching faces, for Black and Asian individuals compared to white individuals, sometimes 10 to 100 times higher, depending on the algorithm and the specific task.
That's a massive disparity, with serious implications if used for law enforcement or access control.
Absolutely. Another example involved object recognition systems. Researchers found they performed worse at identifying common household items in photos from lower-income, non-Western countries compared to items from wealthier Western households. Why? Likely because the massive data sets scraped from the internet used for training were heavily biased towards images reflecting Western lifestyles. The key takeaway for you is simple. Biased data leads to biased algorithms. It's almost inevitable without careful mitigation.
That's incredibly important. It's not magic, it reflects the data. Okay, second risk. Privacy invasion and data security.
Computer vision systems, by their very nature, often involve capturing and analyzing vast amounts of visual data. This data can be intensely personal and sensitive images of our faces, our homes, our activities. Often this collection happens passively, without the explicit, informed consent of everyone being captured, especially in public spaces.
So just walking down the street, I could be captured by numerous cameras feeding into different systems.
Potentially, yes. This mass collection raises fundamental privacy concerns. Where is this data stored? Who has access to it? How long is it kept? Furthermore, these large databases of sensitive visual information become extremely attractive targets for cybercriminals. A data breach could expose highly private aspects of people's lives.
Like those facial recognition datasets built by scraping millions of photos from social media sites without users' explicit consent for that purpose.
That's a prime example. Or think about the proliferation of always-on smart home cameras, video doorbells, even cameras in cars. They are constantly capturing visual information in and around private spaces. While offering convenience or security benefits, they also create persistent records of our lives, raising complex questions about control and potential misuse.
Which leads directly to the third major concern, mass surveillance and social control.
This is perhaps the most dystopian fear associated with computer vision. The combination of ubiquitous cameras, public CCTV, private security cams, body cams, drones with powerful automated analysis capabilities like facial recognition enables potentially pervasive, persistent, and low-cost surveillance by both governments and corporations.
Lowering the cost and effort of monitoring large populations.
Drastically. This capability could have a chilling effect on fundamental rights like freedom of speech, association, and assembly, as individuals may alter their behavior if they believe they are constantly being watched and analyzed. It provides powerful tools for monitoring and potentially controlling populations.
We've seen reports of authoritarian states using this technology explicitly for monitoring ethnic minorities or suppressing dissent.
Yes, those are stark examples. But even in democratic societies, the increasing deployment of facial recognition by law enforcement at protests, or its proposed use in public spaces, sparks intense debate about the appropriate balance between security and civil liberties. Where do we draw the line?
A critical question. Okay, back to the black box. Accountability and transparency. If something goes wrong, who's responsible?
The opacity of many complex deep learning models creates a significant accountability vacuum. When an AI system makes a critical error causing harm, a self-driving car crash attributed to a perception failure, a medical AI misdiagnosis leading to improper treatment, it can be incredibly difficult, sometimes impossible, to definitively determine the root cause or fairly assign liability.
Because you can't easily interrogate the model's reasoning.
Right. Was it faulty data? A flaw in the model architecture? An unexpected interaction? Without transparency into the decision-making process, it's hard to learn from mistakes, rectify flaws, or provide recourse for those harmed. This lack of accountability further erodes trust.
That example you gave earlier, an AI predicting pneumonia risk based on the type of X-ray machine used, not the patient's lungs. That's a perfect illustration of a dangerous shortcut a black box might learn, which would be invisible without transparency.
Exactly. It learned a spurious correlation from the data that happened to work well on the training set, but is clinically meaningless and potentially harmful. We need methods to audit and understand these models.
Finally, the risk of fraud and malicious misuse, the tech being turned to bad ends.
The same powerful capabilities can be weaponized. Generative models, which we'll discuss more, can create hyper-realistic deepfakes, fake videos or audio recordings used for spreading misinformation, political manipulation, fraud, or personal harassment.
That seems incredibly dangerous in today's information environment.
It is. Recognition systems can also be targets. Criminals might use sophisticated masks or manipulated images to fool facial recognition systems for identity theft or to gain unauthorized access. There were reports of criminals using realistic masks to commit unemployment fraud by fooling identity verification systems.
And you mentioned a hypothetical casino using facial recognition to identify and perhaps exploit novice gamblers.
That highlights the potential for subtle manipulation. The technology could be used in ways that disadvantage consumers or citizens without their knowledge. The potential for misuse is broad and requires constant vigilance.
So the critical takeaway here seems to be that these technical and ethical challenges are not separate issues. They're deeply interconnected.
Absolutely. The societal problem of algorithmic bias is a direct result of the technical problem of biased training data and potentially flawed model architectures. The accountability problem stems from the technical limitation of model opacity. Therefore, achieving responsible AI or ethical AI isn't just a matter for philosophers or policymakers, it's fundamentally an engineering and data science challenge.
Meaning it needs technical solutions.
Yes. It requires rigorous methodologies for data governance, bias detection, and mitigation techniques built into the model development process, robust testing across diverse scenarios and populations, and developing more interpretable models or explanation techniques. It requires embedding ethical considerations into the design and engineering workflow from the very beginning.
And that pacing problem means companies and regulators are constantly playing catch-up.
Right. It creates strategic uncertainty. Companies might invest heavily in a technology only to face sudden regulatory hurdles or public backlash later. This fragmented, evolving landscape demands proactive engagement, transparency, and a commitment to building systems that are not just powerful, but also fair, accountable, and trustworthy to earn and maintain that societal license to operate.
It's a huge balancing act. Okay, despite these challenges, the field is racing ahead. Let's look over the next horizon. What future trajectories and long-term potential does computer vision hold? What emerging tech paradigms are shaping what comes next?
There are several really exciting frontiers. I'd highlight three interconnected paradigms that are driving the future. First is the rise of generative vision, from analysis to creation.
Okay, explain that shift.
Traditionally, as we've discussed, CV has been analytical input and image, output information about it. This is the cat. Generative vision flips that. It takes some input, maybe random noise, maybe a text description, and creates a new synthetic image as output. Create an image of a cat wearing a hat.
So AI not just seeing, but imagining and creating visual content. And the main tech behind this is GANs, generative adversarial networks.
GANs have been hugely influential here, yes.
No.
A GAN basically pits two neural networks against each other. You have a generator network that tries to create realistic-looking images from scratch, starting from random noise. And you have a discriminator network that acts like an art critic. Its job is to look at images, some real and some fake, from the generator and decide which are which.
So they're competing, like a forger and a detective.
Exactly. It's an adversarial game. The generator constantly tries to get better at fooling the discriminator, and the discriminator constantly tries to get better at spotting the fakes. Through this competition, the generator learns to produce incredibly realistic and high-fidelity images. State-of-the-art models like StyleGAN can create photorealistic faces of people who don't exist that are often indistinguishable from real photos to humans.
The most talked about use is deepfakes, which has negative connotations. But what are the constructive strategic applications of this generative power?
Arguably the most important positive application is synthetic data generation. GNs and other generative models like diffusion models now can create vast amounts of high-quality, diverse, synthetic training data.
Fake data to train other AIs, why is that useful?
It helps solve the data scarcity bottleneck we talked about earlier. If you need more examples of a rare medical condition or a dangerous driving scenario, You can generate synthetic examples instead of waiting to collect real ones. Crucially, this synthetic data comes perfectly labeled automatically, and it's a powerful tool for mitigating bias. You can intentionally generate a perfectly balanced data set with equal representation across different demographics, something incredibly hard to achieve with real-world data collection.
So what does this mean for you if you're developing AI? Faster, cheaper, potentially fairer training?
Exactly. It bypasses many limitations of real-world data. Generative models are also great for image enhancement and translation. Things like super resolution, making low-res images sharp, in-painting, realistically filling in missing or corrupted parts of an image, style transfer, making photo look like a Van Gogh painting, or even converting day scenes to night scenes, like with CycleGAN.
This sounds profound. It really shifts CV from being just a passive observer to an active participant, a creator in workflows for design, entertainment, simulation, data science.
It absolutely does. It's a massive expansion of capabilities. The second major paradigm is multimodal intelligence, the convergence of vision and language.
Multimodal, meaning multiple types of data together.
Precisely. Humans experience the world through a fusion of senses, vision, hearing, touch, language. We seamlessly integrate this information. AI, traditionally, has been largely unimodal, separate models for images, separate models for text, etc. Multimodal AI aims to build unified models that can process, relate, and reason about information from multiple modalities simultaneously.
And the biggest trend here is vision language models, VLMs, combining sight and text.
Yes, that's the most prominent area right now. These models, often built on the powerful transformer architecture, are trained on absolutely massive data sets of images paired with their textual descriptions. Think billions of image caption pairs scraped from the web.
And this training allows them to learn connections between what things look like and how we talk about them.
Deep semantic connections. They learn that the pixels forming a furry creature with pointy ears correspond to the word cat, but also related concepts like pet, animal, mammal, etc.
What new abilities does this unlock that unimodal systems couldn't do?
Really powerful stuff. Visual question answering, VQA, is a big one. You give the model an image and ask a natural language question about it, like what color is the car parked behind the tree or how many people are sitting at the table. The model needs to understand the question and ground it in the visual content to answer.
That requires true understanding, not just pattern matching.
It does. Other capabilities include automatic image captioning, generating rich, human-like descriptions for an image, and advanced visual reasoning. The latest state-of-the-art VLMs, like Google's Gemma 3, Meta's Llama 3.2 Vision, or Qwen 2.5 VL, can do amazing things like interpret complex charts and graphs within documents, understand the layout of a page, even analyze activities and relationships unfolding over long videos.
And this connection also powers the text-to-image models everyone's playing with. DALL-E, Midjourney.
Exactly. Models like DALL-E leverage this learned vision language connection. You give them a text prompt, an astronaut riding a horse on the moon in a photorealistic style, and they generate a novel image matching that description.
Strategically, this feels like a huge leap towards more general, human-like AI.
It is. By grounding language in visual reality and giving vision a linguistic framework, these models can handle ambiguity and context much better. It's paving the way for much more natural, intuitive, and capable human-computer interaction.
Okay, paradigm 3, reconstructing reality. The rise of real-time 3D modeling, moving beyond flat 2D images.
Right. The goal here is to take visual input, usually from cameras, and reconstruct a full three-dimensional model of the scene or object, essentially creating a digital twin of the physical world.
How is this different from traditional 3D graphics?
Traditional 3D graphics usually involves artists manually creating models. This is about automatically inferring the 3D structure from sensor data, primarily images or video. The field has progressed from older, slower methods to newer AI-driven techniques.
And the revolutionary tech here is NERS, neural radiance fields. What are they?
NERSs have been a game changer in the last few years. A NERF uses a neural network to learn a continuous representation of a scene's volume and how it emits light in different directions. You train it by showing it a set of 2D images of the scene taken from different viewpoints.
So you feed it photos from different angles.
And the neural network learns this internal 3D representation. Once trained, the NERF can render incredibly photorealistic new views of the scene from any arbitrary viewpoint, even viewpoints it never saw during training. It's amazing at capturing complex geometry and really subtle lighting effects like reflections and translucency.
That sounds computationally intensive. Is the focus also on making this happen in real time?
Yes, that's a major research push. developing systems that can perform this kind of 3D reconstruction live using a video feed as input. This requires highly optimized algorithms. It's sometimes aided by specialized sensors like event cameras.
Event cameras, what are they?
Unlike traditional cameras that capture full frames at fixed intervals, event cameras have pixels that only report changes in brightness asynchronously. They're very good at capturing fast motion with high temporal resolution and low latency, which can be beneficial for real-time 3D tracking and mapping. SLAM. We're already seeing commercial software like DJI Terra for drones that can create detailed 3D maps and models from aerial imagery, sometimes even in real time during the flight.
This ability to create dynamic 3D models of the world seems foundational for, well, lots of things. Robotics, simulation.
Absolutely foundational. For robots to truly navigate and interact intelligently and safely within complex, unstructured environments, they need an accurate, constantly updated 3D map of their surroundings. It's crucial for advanced simulation environments, and perhaps most significantly, it's the underpinning for the next generation of computing interfaces.
Okay, so let's connect these dots. We have generative vision, creating content, multimodal AI, understanding vision and language together, and real-time 3D reconstruction mapping the world. What does this convergence mean for long-term societal impact? It sounds like that line between the physical and digital worlds is going to get really blurry.
That's exactly where it's heading. And the primary interface for experiencing this blur will likely be augmented reality, AR. For decades, our main digital interface has been the 2D screen phones, tablets, monitors. AR represents the next major platform shift, moving digital information off the screen and seamlessly overlaying it onto our view of the real world through smart glasses or headsets.
And computer vision is essential for AR to work at all.
Indispensable. For an AR device to place digital objects correctly and realistically into your view of the world, it must first see and understand the geometry and semantics of your physical surroundings using computer vision mapping surfaces, recognizing objects, tracking your position. CV is the sensory system for AR.
This sounds like it could transform almost everything. Education, healthcare.
Imagine the impact. In education, students could walk through a historically accurate, interactive 3D reconstruction of ancient Rome overlaid onto their school playground. Medical students could practice surgery on realistic virtual patients overlaid onto physical mannequins. In healthcare, a surgeon could see a patient's live vital signs, 3D MRI scans, or the precise location of blood vessels overlaid directly onto their view of the patient during an operation, guiding their instruments with superhuman precision.
And in industry or commerce?
A field technician repairing complex machinery could be guided by remote experts with holographic instructions and diagrams overlaid onto the actual equipment. Consumers could use AR to realistically visualize how furniture would look in their living room before buying it, or virtually try on clothes. The possibilities are vast.
But this power, especially with always-on, head-worn cameras constantly scanning our surroundings for AR, must amplify those ethical challenges we discussed earlier.
Massively amplified. A world saturated with AR devices raises unprecedented privacy concerns. What are these always-on cameras recording? Who has access to that constant stream of visual data about our lives, our homes, our interactions? There's also the potential for increased social isolation, as people might retreat into their own personalized, digitally augmented realities.
And just information overload.
Or
Or inequality.
Yes, the risk of cognitive overload from a constant barrage of digital information. And if these sophisticated AR devices are expensive, their widespread adoption could significantly exacerbate the digital divide, creating new forms of inequality between those who have access to this enhanced reality and those who don't. These are critical societal issues to address proactively.
Definitely. Lastly, let's revisit the convergence of vision and language. You said historically they were treated as separate AI domains.
They largely were. CV dealt with messy, continuous, high-dimensional pixel data from the physical world. NLP dealt with discrete, symbolic word data and the complexities of human language, ambiguity, context, sarcasm. Plus, text data was generally easier to collect and label in vast quantities than visual data.
But the future is integration, not separation.
Absolutely.
Yeah.
The success of the transformer architecture born in NLP in the vision domain, ViT, was a huge sign. The rapid rise of multimodal models that process vision and language jointly confirms it. The future of truly intelligent AI isn't about creating separate siloed senses, but about building integrated systems that can see, read, listen, and reason together holistically, much more like humans do.
And this leads to that really profound concept you mentioned, the reality API, an interface to the physical world. Break that down.
Think of it like this. Real-time 3D reconstruction, like NERFs and SLAM, provides the underlying geometric map of the world. Multimodal AI, like VLMs, adds the semantic layer. It understands what things are in that map and allows us to query it using natural language. And generative vision gives us the tools to potentially write to or modify this digital layer overlaid on reality.
So, delivered through AR glasses, we could not only ask questions about the world, what's that building, but maybe even add digital information to it. Leave a virtual note for my friend on that restaurant door.
Exactly. It moves beyond information retrieval to potentially information creation and modification layered onto the physical world. This fundamentally alters our concepts of place, information sharing, even reality itself, and it raises enormous questions. Who controls this digital layer? What are the rules for adding content? Digital property rights in AR, visual pollution. Control over the API to our shared world becomes a critical issue.
And it also flips the data flow. Instead of humans actively creating digital content, the environment itself becomes the data source.
Yes, that's a key long-term implication. In a world of pervasive sensors constantly capturing visual data, the environment becomes the primary generator of information, often passively and continuously. This enables ambient intelligence systems that anticipate our needs and adapt based on constant observation.
Which sounds convenient, but also potentially the ultimate erosion of privacy if not managed carefully.
Precisely. It promises unprecedented convenience, but also necessitates extremely robust ethical guidelines, privacy protections, and governance frameworks to prevent misuse and ensure human autonomy isn't undermined. This requires a societal conversation, not just a technical one.
A powerful and slightly unnerving vision of the future. Okay, given this complex landscape of promise and peril, what are the key strategic recommendations for different stakeholders? Let's start with business and technology leaders. What should they be doing?
For business and tech leaders, a few key things. First, focus on immediate ROI through automation of eyeballing. Don't try to boil the ocean immediately. The clearest, most immediate returns often come from automating those high-volume, repetitive visual inspection tasks. Quality control of production lines, inventory scanning in warehouses, document processing with OCR, safety monitoring. These have tangible business cases and can fund more ambitious long-term R&D. Second, treat data as a core strategic asset, not an afterthought. In the AI era, proprietary high-quality data is often the most defensible competitive advantage. Look at Tesla's fleet data or Amazon's shopper data. Build that data moat. Invest heavily in data governance, robust data pipelines, efficient annotation processes, and seriously explore synthetic data generation to overcome scarcity, speed up development, and mitigate bias. Third, prepare for the next wave of innovation. Don't just optimize for today's analytical CV. Start building capabilities and running pilot projects in those emerging paradigms. Multimodal models for enhancing customer service or understanding complex reports, generative vision for accelerating product design, creating marketing content, or building better simulations. Early adoption here will be key to staying competitive. And finally, maybe most importantly, embed responsible design into engineering culture, not just a compliance checklist. The ethical risks we discussed, bias, privacy, accountability, are genuine business risks. They can lead to reputational damage, legal liability, loss of customer trust, and regulatory fines. Responsible AI needs to be baked into the engineering process from day one.
How? What does that look like practically?
Mandating rigorous bias testing across diverse populations, implementing privacy by design principles in data handling, establishing clear processes for human oversight and intervention, especially for high-stakes decisions, human in the loop, fostering a culture where engineers feel empowered to raise ethical concerns. Proactive, responsible design is the best defense against future problems.
Okay, sound advice for leaders. What about for investors looking at this space? Where should they focus their capital?
For investors, first, evaluate companies beyond just model accuracy benchmarks. While technical performance matters, the long-term winners might be those with the strongest data ecosystem. Look at their ability to acquire unique data, process it efficiently, leverage it to improve their products, and create that positive feedback loop, the data network effect. That's often more sustainable than just having the slightly better algorithm today. Second, invest in the enabling infrastructure, the picks and shovels. The growth of computer vision across all industries will create massive demand for the underlying tools and infrastructure. There are huge opportunities in companies providing the essential building blocks. Specialized AI hardware, GPUs, NPUs, edge AI chips, cloud platforms optimized for AI, edge computing solutions, data annotation services, synthetic data platforms, MLOs tools. Third, carefully assess regulatory and ethical risk exposure. That pacing problem between tech and regulation creates market uncertainty. Evaluate how exposed a potential investment is to future regulatory headwinds, especially in sensitive areas like public facial recognition or biometric data handling. Companies that demonstrate a proactive, transparent approach to ethics and privacy may represent more sustainable long-term investments.
Makes sense. And finally, for policymakers and regulators grappling with this rapidly evolving technology, what should their priorities be?
This is tough given the pace. First, address the pacing problem with agile governance approaches. Traditional, slow-moving legislative processes struggle to keep up. Explore more adaptive frameworks, things like regulatory sandboxes, where companies can test innovations under supervision, outcome-based regulations, or co-regulation models involving industry standards bodies. Focus on broad, enduring principles, fairness, accountability, transparency, safety, security, rather than highly specific technical rules that will quickly become obsolete. Second, prioritize legal clarity on privacy, consent, and liability. There's huge legal uncertainty right now. We need clearer rules around the collection, use, and retention of visual data, especially sensitive biometrics. What constitutes meaningful, informed consent in an era of passive, ambient data collection? We need clearer legal frameworks for determining liability when autonomous systems cause harm. This uncertainty hinders responsible innovation. Third, actively foster public dialogue and build societal acceptance. The deployment of technology this powerful cannot be decided solely by technologists and corporations. Governments have a crucial role in fostering broad public debate and education about computer vision, its benefits, and its risks. We need to collectively establish societal norms and potential red lines for its use, especially in public spaces or for critical functions. Democratic engagement is essential for building trust and aligning the technology's trajectory with societal values. And fourth, incentivize responsible innovation. Use public funding, tax credits, and other policy levers to actively support research and development into beneficial and responsible AI. This means funding work on explainable AI, XAI, to combat the black box problem, developing better techniques for bias detection and mitigation, advancing privacy-preserving machine learning methods like federated learning or differential privacy, and promoting research into AI safety and robustness.
So, bringing this all together, what's the final perspective, the concluding outlook on the future of computer vision?
The big picture is that computer vision isn't just another software upgrade. It represents a truly fundamental technological shift, arguably on par with the internet or mobile computing in its potential impact.
How so? What makes it that fundamental?
Those earlier revolutions primarily untethered information, making it accessible anywhere, anytime. Computer vision is untethering computation itself from the screen, allowing it to directly perceive, understand, and increasingly interact with the physical world around us. It's giving computation eyes, and soon, the ability to act based on what it sees.
And this journey we've traced from basic pixel analysis towards this vision of ambient multimodal intelligence interacting with the real world that's going to be a defining narrative for the coming decades.
I strongly believe so. The technology's potential to boost productivity, accelerate scientific discovery, improve health outcomes, and enhance our quality of life is undeniable. It offers tremendous promise.
Yet, as we've discussed extensively, its capacity to erode privacy, amplify bias, enable new forms of control, and be misused is equally pertinent. That duality is key.
It's the core tension. The challenge ahead isn't about stopping progress that's likely impossible and probably undesirable. The challenge is about steering it wisely.
Moving from being reactive to problems after they emerge to being proactive and deliberate in how we design and deploy these systems.
Exactly. It requires conscious, thoughtful design choices. It means harnessing the incredible power of this algorithmic eye, but doing so with the wisdom to understand and respect its limitations, and crucially, with the foresight to embed human values, fairness, accountability, transparency, respect for autonomy deep into the code and the systems themselves.
So the future is undoubtedly visual. The question left for all of us, for you listening, is what do you want that future to see, and how will you play a part in shaping that vision?